Alright guys, this is for me. It's for a class discussion 2, modules 7 and 8, and statistics and kinesiology class. Science, statistics, and deception. Ooh, okay. We like to read out loud when we're falling asleep, but this is actually a little more interesting. Alright, here we go. This is by John C. Baylor, 3, MD, PhD, and guess where he lives? He happens to hang out in Washington, D.C. I don't know, I think this is from the 80s, so it's at the bottom. We'll see later. Alright. Some common scientific practices cannot quite be called lying, though they are potentially and sometimes deliberately deceptive. Some examples are the failure to explain to readers all the weaknesses in data, statistical testing of post hoc hypotheses, fragmentary or selective reporting of findings, and reporting as negative a study has insufficient chance of detecting an effect. The first step towards controlling potential problems is a redefinition of ethical standards to bar readily avoidable as well as deliberate deception. Other remedies include substantially greater restraint in the use of questionable practices, full disclosure and justification each time these practices are used, and greater skepticism by readers. Pressures to publish tend to promote deceptions. A broadened concept of ethical standards in science should be reflected in training programs and in the structure of scientific rewards, including a sharply reduced emphasis on publication as an end in itself. I agree. Previous discussion was kind of about that, and I kind of went off on that right there, how there's a lot of pressure to publish, publish this in something, scholarly article or something. Publish something, darn it! Okay, we're continuing on to the main article. In science, lying is condemned, even by some of its few practitioners. Deliberate or careless deception, short of lying, however, seems to be universally accepted and sometimes even promoted as a part of the culture of science. I do not suggest that scientists as a group are careless, venal, or otherwise depraved. They may even be more above the human average in developing and adhering to detailed, albeit tacit, standards of professional conduct. Those who are clearly violators are drummed out of our ranks loudly and publicly. But what about less clear-cut deception? My thesis is that our professional norms are incomplete and that several kinds of widely accepted practices, Table 1, should also be widely recognized as potentially deceptive and harmful. Some of these practices also have much value, but at times they are inappropriate and improper, and to the extent that they are deceptive, unethical. The scientific method is fundamentally concerned with the process of inference, generally from data that are necessarily inaccurate to some degree, incomplete, drawn from small samples, or not quite appropriate for a specific task. Inference, that is, drawing conclusions or making deductions from imperfect data. We'll be asked that a few more times. Inference, that is, drawing conclusions or making deductions from imperfect data, provides most of the excitement and intellectual ferment of science. Scientific rewards are probably more closely related to valid inferences established into such related activities as imaginative hypotheses formulated, elegant experiments designed and conducted, or new methods developed. The rewards for publishing a first-class inference can include income, position, power, professional status, and the respect of colleagues. Such rewards may sometimes count for more than self-respect and the joy of discovery. We must therefore be attentive to scientific norms and activities that may distort the processes of inference. An example of deceptive practices is the statistical testing, such as the calculating of p-values. Talked about that in the last discussion too. P-values or statistically significant. You gotta say statistically. P-values, very big deal. Alright, an example of deceptive practices is the statistical testing, such as calculating p-values of post hoc hypotheses. It is widely recognized that t-tests, chi-square tests, and other statistical tests provide a basis for probability statements only when the hypothesis is fully developed before the data are examined in any way. If even the briefest glance at a study results moves the investigator to consider a hypothesis not formulated before the study was started, that glance destroys the probability value of the evidence at hand. Certainly, careful and unstructured review of data for unexpected clues is a critical part of science. Such review can be an immensely fruitful source of ideas for new, before the fact hypotheses that can be tested in the correct way with other new or exciting data, and sometimes findings may be so striking that independent confirmation by a proper statistical test is superfluous. I don't know what that means. Statistical tests are also used sometimes in non-probability ways as rough measures of the size of an effect rather than to test a hypothesis. An example is the column of p-values that sometimes accompanies a table comparing the pre-treatment characteristics of patient groups in a randomized clinical trial. When either the test itself or the reporting of the test is motivated by the data, a probability statement such as p is less than 0.05 is deceptive and hence damaging to inference. When either the test itself or the reporting of the test is motivated by the data, a probability statement such as p less than 0.05 is deceptive and hence damaging to inference. We'll have to read more about that. Other potential problems are the selective reporting of findings and the reporting of a single study in multiple fragments. These practices can obscure critical aspects of an investigation so that readers will misjudge the evidence. The evidential value of the data presented. Such reporting may be deceptive, whether deliberately or accidentally. On the other hand, these practices sometimes have positive value that should be preserved. For example, they can facilitate the task of both the investigator and the user when a demand for monolithic analysis might seriously delay or frustrate the process of both. I'm frustrated. Negative conclusions of low statistical power, p equals 0.05. That is, reporting that no effect was found when there was a little chance of detecting the effect can also distort inference, especially when investigators do not report on statistical power. The concept of power is formally defined in terms of the random variability of results that is inherent in a specific combination of data structure, sample size, statistical models, and analytical method. But I believe that the concept should be substantially broadened to include the likelihood that a particular effect would be detected and reported if it were present to some specified degree. Such an analysis rarely accompanies negative findings, and readers may be left with an unjustified sense that an effect not demonstrated is an effect not present. Again, however, there are counter-arguments. A report with low power gotta be greater than 0.8. If you're less than 0.8, your sample size might be a little small, you know what I'm saying? Alright, again, however, there are counter-arguments. A report with low power may be better than no report and no power. That's important. Scientists out there, we want to know something. Just give me something to work with. Or meta-analysis of several low-power reports may come to stronger conclusions than any one of them alone. We gotta know. Reporting negative studies of low power can create ethical problems, but those problems may be largely mitigated if the low power is accurately and clearly reported as well. Too many scientists resist the objective reporting of this kind of weakness in their work, and pressure for strong results may be greatest during the formative years of graduate training and career entries. Thus, we may be training new scientists in unethical methods. Despite the occasional useful roles of these and other practices listed in Table 1. Let's read those in Table 1. Failure to deal honestly with readers about non-random error, bias, post hoc hypotheses, multiple comparisons and data dredging, inappropriate statistical tests and other statistical procedures, fragmentation of reports, low statistical power, suppressing, trimming, or adjusting data or undisclosed report, repetition of unsatisfactory experiments, and selective reporting of findings. Each can seriously distort the processes of inference and should therefore be an object of concern. Where the practices have legitimate applications, they should, of course, be used, but even then, they should be fully and explicitly disclosed by the investigator, justified in some deal, and accepted with caution by readers. A combination of restraint in their overall use, limiting their use to clearly appropriate situations, providing full disclosure and justification, and maintaining the reader's skepticism will help to diminish the frequency and severity of ethical problems. Full disclosure here means more than a few words buried in the fine print of a methods section. It means not just that the author sent a message, but the author also worked to ensure that the message is received and correctly interpreted by the readers. There are parallels here to the evolving requirements for informed consent by experimental subjects. Pressures to publish can be great and may account for many of the abuses suggested in Table 1. I fear that even the constrained use of these potentially damaging practices will leave attractive loopholes for any army of ambitious practitioners of science, each feeling great pressure to publish, who will rush in to explain why his or her situation is different, why full disclosure is inappropriate, and so forth. I am convinced that scientists, and society as a whole would benefit from substantially broader concepts, ultimately based on the need to protect the processes of inference about ethical standards and violations in science. Wow. Hooah! De Niro? Maybe. Alright, so that was Science, Statistics, and Deception. That was by John C. Baylor III, MD, PhD, Washington, D.C. Maybe we get a date on this, baby. From the Office of Disease Prevention and Health Promotion, Department of Health and Human Services, Washington, D.C. February 1986, The Annals of Internal Medicine, Volume 104, Number 2. Cool! There we go. There goes my works cited. Alright, love you guys. That was good. Science, Statistics, and Deception. Or that's my my presidential State of the Union of Science. Alright, check you later. Buck Hill, you better comment, alright? Because I'm about to upload this thing. I want to hear something good. As you can see, maybe I did add a little bit of decorations up in here. Alright, that one's really just to cover some holes that I had for that speaker, because there's some lack of studs or something back there. It's weird. Yep, there's my bike. And 3 screens helps out a lot. Throw something over there, throw something over there while you're reading over there, and then you could type while you're reading there. And yeah, surround sound speaker. Yeah, very nice, very nice. Pretty good, comfortable setup here. Alright, like I said, love you guys. Hope you find that interesting. It's really for me, so I can just listen to it again. But it's really good. Really good. The pressure to publish, right? See ya.